Hi everyone, I'm Pranjay Shyam and I'll be presenting our paper Lightweight Thermal Super Resolution and Object Detection for Robust Perception in Adverse Weather Conditions. So before moving forward, I would like to elaborate upon the problem definition and scope. So computer vision based advanced driving assistance systems perform poorly in adverse weather conditions such as rain, fog, snow, and night, and even when there is water droplet or flare within the image. Now, this results in failure of underlying perception algorithms such as semantic segmentation, object detection, depth estimation, and simultaneous localization and mapping due to occlusion of relevant information. Utilizing an auxiliary sensor capturing infrared spectrum of light can help alleviate the sensitivity of RGB-based perception algorithms since such sensors are unaffected by external illumination and environmental factors, making them an ideal replacement to RGB cameras for adverse weather conditions. Despite the inherent advantages of thermal imaging sensors, their integration into the perception stack of vehicles has been hindered by issues such as poor information capture in clear conditions, high sensor cost, and low image resolution. Current state-of-the-art approaches follow either a fusion-based approach or utilize two different networks for different modalities. This limits their performance in scenarios where information content of thermal or RGB image is inadequate. Example, stationary vehicles in snowy conditions. To address these limitations and challenges, we propose five contributions in this work. First, we propose a switching mechanism that ensures dynamic utilization of thermal images in the event of poor RGB cameras and enabling a shared object detection algorithm. Second, to ensure compatibility between the thermal and RGB modalities, we propose a projection function that transforms the thermal image into a compatible RGB space. Third, towards enabling a low-cost solution, we utilize a low-cost, low-resolution thermal imaging sensor and increase its resolution by integrating a lightweight super-resolution algorithm that allows for hardware-efficient design. Fourth, to improve the feature information captured by the lightweight feature extraction backbone of an object detector, we propose a bidirectional feature pyramid network. Finally, we utilize the object detection algorithm during the optimization process as well to reduce adversarial patterns which would be present in the super-resolved images. So, given a low resolution thermal image along with the aligned high resolution RGB image, our objective is to leverage the thermal image in the event of poor RGB quality, which would be used as an input to the object detection algorithm. Towards this, a lightweight super resolution algorithm is proposed to upsample by a factor of 4 the thermal image, which is subsequently projected into the RGB space for utilization by the shared object detector. We provide a holistic overview of the proposed methodology in this page. Now, we first focus on the switching functionality. So, the demand for lightweight and computationally efficient solution is paramount in the realm of image quality assessment for optimal performance of object detection algorithms. We propose a pragmatic approach to swiftly detect potential image degradation before integrating the input into the underlying object detection pipeline. Towards this, we focus on weather-induced corruptions, including flare, snow, fog, rain, and low-light scenarios, wherein we observe that these often lead to oversaturation, creating regions of intense brightness within the image. By designing a basic filter, we can identify distinctive peaks in the intensity histogram of the RGB image, which are indicative of the predominantly intensity values, and average to determine the highest peak. Now, by employing a thresholding mechanism, we can classify whether the given image has been compromised by weather-induced degradation. So, this solution offers a simple and effective mean to assess image quality, thereby ensuring the robustness and accuracy of downstream object detection tasks even in challenging weather conditions. Focusing on lightweight super resolution, given the presence of weather degradation affecting an RGB image quality, we select this branch to perform lightweight super resolution on an input low resolution thermal image. We streamline the computational load of the super resolution network by tactically downsampling the input image across the channel dimension through staggered convolutional operations. Recognizing the inherent ill-posed nature of such low resolution upsampling, wherein multiple high resolution solutions can coexist, we utilize transformer based super resolution architectures for adaptively capturing intricate non local feature correlations. However, utilizing a transformer based architecture results in utilizing the self-attention mechanism, which has a quadratic computational complexity, which poses a challenge towards a lightweight super resolution design. To reduce the computational complexity, we introduce a novel convolutional-based alternative to the self-attention mechanism. This approach facilitates the extraction of multi-scale features that subsequently undergo the dynamic feature selection. This feature selection ensures the assimilation of non-local feature interactions, which are then synergistically augmented with the power of convolutional channel mixing strategies, which enables the efficient extraction of pertinent local features. Now, to ensure capturing of long-range dependencies while circumventing the computational challenges posed by self-attention mechanism, we leverage the feature pyramid networks tailored to cater to diverse scales of contextual information. We provide a basic overview of the proposed approach above and begin by the process by constructing a robust feature pyramid network architecture leveraging channel splitting techniques, thereby facilitating the extraction of multi-scale features across four distinct scales. These diverse scale-specific features are then refined through a combination of operations that balance information preservation and computational efficiency. We now present some qualitative results of the proposed upsampling algorithms and compare it with state-of-the-art approaches. Now elaborate upon the learnable projection function. So as an alternative to fusion-based approach or having distinct weights for different modalities, we propose a solution to integrate thermal images directly into the RGB-based object detection pipeline seamlessly. So this is achieved via a learnable projection function that orchestrates the transformation of thermal image statistics into a format that seamlessly aligns with the RGB space. This operation is performed via channel-wise mean variance transfer. For each channel in the RGB space, we compute the mean and variance as learnable parameters, and then we use it to transform the grayscale information for the thermal image into the RGB space. To ensure that optimizing these parameters does not break the training cycle due to boundary conditions when sigma equals to 0, we include a fixed bias of 1 e to the power minus 3 as epsilon. We now provide some qualitative results on how the projected RGB image looks for a given thermal image using the proposed mechanism. We now elaborate upon the bidirectional feature pyramid network, which is used for enhancing the feature extraction and representation capabilities of the object detection algorithms. Towards this, we propose modifications within the feature pyramid network to improve the feature representation within the single stage object detectors while requiring less computations. So specifically, we propose performing 1x1 convolutions on the multi-scale features before upsampling, which results in the same output resolution as traditional FPN while consuming fewer parameters and floating point operations. Second, we refine the multi-scale features using group-wise convolutions, which instead of using multi-scale features for performing object detection, following prior real-time object detection algorithms, we use the aggregated feature map to compute the bounding box of objects of interest. We now provide some quantitative results of the state-of-the-art performance for super-resolution algorithm on the dense and FLIR datasets. We also include the influence of integrating the object detection algorithm, in this case YOLO-X tiny version, during optimization on the performance of state-of-the-art super-resolution algorithms on the same dense and FLIR datasets, with detection performance included as well on the right. We now provide some qualitative results on the performance of thermal or image-based RGB detector, RGB image-based thermal detector, and the proposed mechanism which seamlessly integrates both the different modalities. Finally, we also provide some qualitative performance of the proposed algorithm on dense dataset with object detection results superimposed on the super-resolved thermal images. Similarly, we perform the same qualitative performance evaluation of the proposed mechanism on the KAIST dataset with object detection results superimposed on super-resolved images. I would now like to conclude my presentation and I would thank you for your attention.